Okay, today I'm going to be going over the problem called field from two charges in 1D. The problem states that 2-point charges lie on the x-axis. A charge of positive 6.35 microcoulombs is at the origin, and a charge of negative 9.76 microcoulombs is at x equals 10 centimeters. What is the net electric field at A? X equals to negative 4.13 centimeters, and B, x equals to 4.13 centimeters, positive 4.13 centimeters. So step one is going to be going over our given values, which I made Q1, which is our charge 1, negative 9.76 microcoulombs, which if you change that to coulombs, which is just dividing this by 10 to the 6th, it'll give you regular coulombs, which is negative 9.76 times 10 to the negative 6 coulombs. That is going to be our charge 1. Charge 2 is equal to 6.35 microcoulombs, which if you divide that by 10 to the 6th, will give you 6.35 times 10 to the negative 6 coulombs, and that's going to be our charge 2. The location of charge 1 is at 0 centimeters, and I went ahead and changed that to meters, which would be 0.1 meters in the x and 0 in the y. And then the location of our Q2 is going to be 0 meters because it's just 0 centimeters anyways. So then you have the location of your test charge 1, which is part A of the question, which is going to be negative 4.13 centimeters in the x and 0 in the y, and we change that to meters. It'd be negative 0.0413 meters in the x and 0 meters in the y. And then for part B, the second test charge is going to be at positive 4.13 centimeters in the x and 0 centimeters in the y. And if you change that to meters, it'll be 0.0413 meters in the x and 0 meters in the y. Okay. And then we move into step 2, which is going over our useful equations. And we only have one in this case, which is E equals to K Q over R squared R hat. And the values in this equation are K, which is equal to 9 times 10 to the 9th, and that is going to be Coulomb's law constant. And Q is the charge of our point or points. And then R is going to be the distance between charges. So this whole thing is called the electric field equation. And that's what we're going to be using in this problem. And then I went ahead and drew a diagram for step 3. So we have our charge 1, this should be charge 1, which is 0.1 meters in the x and 0 meters in the y. So it lies to the right side of this x-axis. Charge 2, this is say charge 2, is 0 meters, 0 on the x, 0 on the y. Just like the problem stated. And then here are two test charges. This would be part A, and this would be part B. And I went over this earlier, but I'll go over it again. This is negative 0.0413 meters in the x, so it's to the left of the origin, and 0 meters in the y. And then this is part B, our second test charge. It is 0.041, positive 0.0413 in the x and 0 in the y. Okay. And now we will move into step 4, which is actually solving the problem. So we take our useful equation in this case, I'm calling it E1 because that's test charge 1, is equal to K times Q1 over R squared minus Q2 over R squared. And it is a minus because if you look back at the graph, which is right here, since this charge is a positive, they'll both be attractive to each other, these 2 points. So if this force is going that way and this force is going this way, this force should be in the positive direction and this force would be in the negative direction. So we are subtracting it because of that. And so we plug in our values, basically. 9 times 10 to the 9th, which is just our K value. And then we plug in our Q1, 9.76 times 10 to the negative 6th. We put that over our R squared. In this case, that distance would just be 0.1 meters, which is the distance from the origin, and then plus the extra distance that our test charge is away from the origin, which would just be plus 0.0413. And you square that, and we're subtracting that by 6.35 times 10 to the negative 6, which is the our second charge, over 0.0413 squared, which is just the distance from our charge 2 to our test charge. And we end up getting these two values from these two values, and we just subtract these two, multiply it by 9 times 10 to the 9th, and we end up getting our first electric field force at the first test charge, and that'd be negative 2.91 times 10 to the 7th Newton over coulombs. So that's what is being felt at this point right here. So now we are going to calculate what the electric field force is, what is felt in this spot right here. So for that, we are going to then again use our electric field equation, and I'm calling it E2, and that would equal K times Q1 over R squared, and this should say plus, because if we look back over here, since this force is in between these two, they would both be attracted to each other, and the forces would be felt together at this point. So it'd be K times Q1 over R squared plus Q2 over R squared. And we plug in our values once again, 9 times 10 to the 9th times our Q1, which is 9.76 times 10 to the negative 6, over, this is a new distance, it'd be our 0.1, which is the distance our charge 1 is away from the origin. And since the new test charge is now 0.0413, it's positive, we will now be subtracting this over and squaring it. And then we add that to we add these two together, and this part is 6.35 times 10 to the negative 6, which is our Q2, and that is over the same distance because they are either way, it doesn't matter. Between the two test charges, they're the same distance away from this Q2, and we end up getting these two values, and we just add these two together, multiply it by 9 times 10 to the 9th, and we end up getting 5.90 times 10 to the 7th Newton over coulombs for the second force being felt at that test charge for the electric field.